Hi, welcome to another session of 4AC work tutorial. Today we want to look at the past exam paper, February 2014, question number 4. Alright, the question reads, a 230 volt 50 Hz AC supply is connected to three loads, load 1, load 2, and load 3, as shown in figure 4.1. We are required to calculate the branch current I1, I2, and I3. Then we want to calculate the real power and reactive power for load 1, load 2, and load 3. Next, we want to calculate the overall complex power. That means these three loads, how do they contribute as far as the supply is concerned. Hence, to determine the overall power factor. And finally, we want to determine the value of the capacitor required to raise the power factor to unity, right, from whatever its value. So this is part A. We shall look at part A first, and we look at part B at another time. Alright, to answer this question, what I do is I have sketched this out again and identify all the loads, right? So if I want to calculate branch current 1, I can use the formula, the voltage across this load, divide by the impedance Z1. Okay, so voltage across the load is 230 volt angle 0, divided by the impedance, which is 100 angle 0. So that gives me a current of 2.3 at an angle of 0 degrees ampere. Now for the second load, because the actual impedance is not really given, so I make use of the other formula where the apparent power is actually the voltage multiplied by the current. So in this case, the apparent power is 1200 kVA divided by the magnitude of the voltage, so it's 230. Right, now the angle here is 0, and this angle is given by the negative of the cos inverse, which is actually negative 53.13 degrees. Remember, S is equals to E multiply the conjugate of I, right? So the angle actually becomes negative. So that gives us a value of 5.2 amps with an angle of minus 53.13 degrees. And finally, I3 is just 230 volt angle 0 degrees divided by the total impedance. Now 65 minus J50, I convert it back to the polar version. That would be 82 angle of minus 37.56 degrees. Oops. That gives me a current of 2.804 ampere, angle at 37.56 degrees. Okay, so that's the three current there. Now the next thing we want to do is to determine the P and Q, the real power and the reactive power of each of the load. The first load is just strictly, I can calculate it using I square R. I is 2.3 square times 100. That gives me a power of 529 watts. Whereas the reactive power is 0. Okay. The second one is I am given the apparent power, which is 1200. So I can make use of the power factor involved. So this will be S cosine theta, which is 1200 times 0.6, which gives me 720 watts. Whereas the reactive is S sine theta, This is 1200 multiplied by 0.8 something, 84. Okay, let me check again. 0. This can just come up to be about 960 kVAR. VAR, sorry. Whereas the last load is can use I square R again. I square R. The R is 65, so current is 2.804 square times 65. That gives me 511 watts. Whereas for the reactive power is I square X. That's 2.804 square multiplied by 50. That's about 399 bars. 393, sorry, 393 bars. Right, so now what's left is for me to add up all the powers, right? So that means 529 plus 720. Now this vase is plus J 960 plus 511 minus, this is negative, minus J 393. So total I'll get 1760 plus J 567 VA. Convert to polar form, I'll get 1849 with an angle of 17.86 degrees VA. Power factor P is cosine of the angle 17.86 degree. It's equals to 0.95 lagging because it's inductive. Okay, so that's part A, part 1, 2, and 3. Now the next part of the question requires us to calculate what extra capacitors I must put across here. What extra capacitor I need to put across here to raise the power factor, to 1, to unity, right? Now at this juncture, it'd be good to draw the power triangle. Now power triangles can be derived from here. Currently, this is the resistive, the real power, which is 1760 VA, and this is the reactive power, which is 567 VA. Okay, and this is the apparent power. The angle here is 17.86 degrees. Now, when we want to improve this to unity, that means we want to introduce a capacitor that will provide us the QC so that it cancels out this, then the power factor will be unity, because then the new S will be at this level, right? In other words, QC, that means the reactive power contributed by the new capacitor, must be the same as the reactive power that we are looking at now, which is 567 VA. This is also equals to E squared over XC, which means that I need an XC of E squared over QC. That's equals to 230 squared divided by 567 VA. That is 93.3 ohms. But XC is also equals to 1 upon 2 pi FC. Therefore, the capacitance required is equals to 1 upon 2 pi F replaced with 50 Hertz and 93.3 ohm. So that will give us a capacitance value of 34.12 microfarad. In other words, we need to add a capacitor in parallel with the load. Yeah, if you want the power factor to be improved to 1. Okay, that's all for part A of question 4, February 2014 past exam paper.